So I'm going to do this Oreo lab with you. I'm going to have all the fun because I'm going to eat the Oreos. But we're going to just walk through what the process was. So what we're trying to decide is, when they say double stuff, do they really mean double stuff? So this is our research question. So is double stuff really twice the filling? That's what we're trying to figure out. So we've got cookies. We're going to take the mass and we're going to figure out how much mass there is in the filling. So let's walk through and think what we should do. So to begin with, we're going to do, and it's going to have paper that I'm going to have these on. So the first thing I'm going to do is I'm going to tare, which is just 0, the balance, and I'm going to do that with the paper. So that's my first thing. And then I'm going to twist off, I'm terrible at this, but we're going to see how it goes. I'm going to twist off one of the wafers. So one of those little chocolate cookie pieces, I'm going to twist it off. And then I'm going to take the mass of that one wafer. Hopefully, that's going to leave me with a wafer and the filling on the other cookie side. So then I'm going to mass the other wafer with the filling. And I'm going to do that for 2 regular and 2 of the double stuff cookies. So let's see what I need to keep down here as my information. So I'm going to come down here. I'm going to get data for just the one wafer, right? And then I'm going to get the mass of the wafer with the filling. And then I'm going to use this information. So I'm going to subtract what just the wafer is away from this value. And I should be able to calculate the mass of the filling. And I'm going to do that with a regular cookie, a double stuffed cookie, and a double stuffed cookie. Okay, so I've got our balance right here. And, come on, you don't have much of a cord, do you? Okay. So, 0 this puppy out. Let me come up here. So, paper on there, 0'd out. You can't see what that is. Now, you can. Okay, so I'm going to 0 it. Come on. You're going to 0? What are you doing? That's the weirdest thing ever. Okay, that's the cheaty way to do it because it's being a poop head. Alright, so here's a regular cookie, and I'm going to just twist off this one wafer. And I'm going to have to write it over here. I'll put it in there in just a second. It's 4.27 grams. Okay? Then I'm going to take the mass of the wafer with the filling. And so that's 7.15 grams. So that's one regular. Okay? Let's just repeat that with the other regular. I did a real good job on that twisting. Let's be truthful. Okay. I didn't do a very good job on that one. Let's see. Okay, there's that wafer. It's 4.5, I bet, by itself. And then 6.84 for the one with the filling. Okay, so now I'm ready for my double stuff. So here's my double stuff. Let's see if I can do better. So that's the wafer. Wafer should be a wafer, right? So that's 4.51 for the double stuff. And then, what is that one? I don't know why there's this dramatic need for me to plop them on there. 10.47. And then I'll do the next one. 4.52. Wow, they're very good. So those are super close. And then that one is 10.48. Okay. You can go away. No. Go away. Alright, so let me fill in, move my cookies. Okay, so let's fill this in. So for the first one, the wafer mass was 4.27 grams, and it was 7.15 grams with the filling. The next one was 4.50 grams, and then it was 6.84 grams with the filling. Now we're getting to the double stuff. 4.51 for the cookie, and 10.47 with the filling, and 4.52. Wow, those are super close, those last ones where I wasn't the best twister. And then 10.48 for the cookie with the filling. So we're going to take our calculator, and we're going to calculate what all these will be. So I'm just going to subtract. This is the weirdest calculator. 7.15 minus 4.27, and I get 2.88 grams for the filling. 6.84 minus 4.5, 2.34. You probably don't need me to talk this out loud as you do it. Okay, 5.96. That's definitely double the filling. And 10.48 minus 5.42. Oh, wow. That seems a little fishy. But you watched me. It was not fishy. Okay, so this is our data, and this is pretty much where we stopped yesterday. Then we had a Google form where that we went in and put our data in with the class data. That's what we did today. And we're going to work with our own data, and we're going to go back, way back in time, and we're going to go back over how to find standard deviation and how to calculate standard error of the mean. Although no one will ever ask you to do that like on a test. But we do need to know where the numbers are coming from, or it's not going to make sense. So this part of what we did, this is my work. So today, I'm going to now come over here, and I'm going to get the information that's going to be the class mean. So I'll do some work down here in just a minute. But what we need is to think about, what do I need to graph? If I'm checking if double stuff is really twice the filling, do I really need to graph the mass of the wafer? I don't, do I? Just the filling, right? Just the filling. So for me, I have regular and the double stuff, and then the whole class had a regular, average, and the double stuff. Okay, so let's put that over there. Oh, I messed this up. Okay, so I have the mass, and this is my mass, and it's going to be the mean. We're going to take the mean of my, that doesn't look very nice, of the mean mass of my regular filling. Okay, so I'm going to do that. And we might as well, let's just do it this way, of the filling, and let's do regular here and double stuff there. That'll save us from writing stuff. Then I'm going to have to get my standard error. So I'm going to put 1 standard error, because that's for me. Then we're going to have the mean mass, and this is for the class of the filling, and we'll get the standard error and use it. So obviously we're going to be doing some bar graphs, and we're going to be doing bar graphs where that we have error bars. Here's the dilemma. I think we were virtual, so heaven forbid, this has been like forever ago that we actually did standard error. Well, to do standard error, you have to find standard deviation. So I'm going to do the steps for that, and I'm going to do it down here so you can see what I'm doing. Don't get wrapped up in it. It's not that big a deal. But the first thing we have to do, and remember these are what I'm working with, just the filling. I need the mean of both of those. Well, this one's super duper easy. In fact, it's kind of scary that I'm not going to have very much that I'm going to be able to do with that. Because obviously there's no difference between the two, so there's going to be 0 standard deviation, which means there'll be 0 standard error. So that's not a bad thing. We'll talk about that. So let's take the mean of these two. So that's just the average. I'm going to do 2.88 plus, I already forgot, 2.34, and then I'm going to divide that by 2. So I end up with 2.61 is my mean. So the way standard deviation works, and it really is one of these things, I don't know how to explain it, and I hope I don't mess it up to make it confusing. If you're only going to talk about your sample, and that's all you're talking about, like you're not going to eventually talk about 130-something data points like we have with our whole class for the population, you're going to use 2 different formulas for standard deviation. So I'm just going to do my sample, and I'm going to do my sample as part of a population. So the way this works is you're going to look for how far away each data point is from the mean. So I take my data point, I subtract the mean, so I'm going to find the difference, then I'm going to square it. And I'm going to repeat that for the next point. Notice that because I'm going to square it, it doesn't matter if it's positive or negative. Then here's the part that's the problem. We're going to go ahead and divide by n, just like you do for a population, because this becomes part of the population. So we're going to divide by 2. If you're just talking sample and you don't mess with your population, it's n minus 1. But remember, nobody cares because you don't have to do this. They would give it to you. Then I take the square root, and that's standard deviation. So let's see what those numbers are. So I have 2.88 minus 2.61. So I get 0.27 squared. So I'm going to have 0.0729 plus 2.34 minus 2.61. Wow. Isn't that interesting, the magic of math when there's just 2 data points? Watch how this goes. Squared. So again I get 0.0729, right? So that's times 2. Well, what am I going to turn around and do with that? I'm going to divide that by 2, right here. Back to this. Then I'm going to take the square root of it. I can't see what I'm doing. And looky there. When you have 2 points, obviously each one is the same distance away from the mean as the other one because there's just 2 points. So this is my standard deviation. You have to know your standard deviation to find your standard error. So standard error of the mean is your standard deviation divided by the square root of how many data points you have. So that's going to be 0.27, because that's my standard deviation, over the square root of 2. No. So 0.19, call it 0.2. Okay, we're going to call it 0.2. Okay, so that's 0.2. So I can come over here and I can fill in. This was the only one I've done for here, right? This one I don't have to do anything, because the difference between them, 0, 0 squared, 0, 0 divided by 2, 0, the square root of 0, 0. So my standard error for this double stuff, because all the data points are the same, is going to be 0, which means your standard error will be 0. So let me fill these in. My mean for my regular is 2.61, and one standard error is 0.2. Right here. Can you see? Yep, right there. My mean for double stuff is 5.96, and I have 0 for standard error. So let me tell you what we did as a class. So when we put our class data in there, here's what we got. We got the mean for the regular is 2.8, and for the double is 6.2. The standard error, one standard error, was 0.3, and the other was 0.6. So what am I going to do with this? Here's the deal. I have to make a decision, and I want to always think about my question. Would it make sense if I graphed, so I'm going to lean this way, the regular for me next to the regular for the class, compared those two, and then compared the double with the double? Is that really what I'm trying to compare? I'm not. I don't want to compare the doubles with each other. That just means how close and what does my data look like compared to the class. I want to look at, for me, my regular, is it half of the double? For the class, my regular, is it half of the double? So that means I'm going to come over here and I'm going to graph regular, double, this is me. Regular, double, this is the class. What I'm actually getting here, this is the mean, right, mass of the filling in grams. Okay with that? So now let's think about what we need to do. I've got 6-ish, a little bit more than 6. This is going to go up. I probably should go like in 2s. So the first thing I do, this is just our normal process. No thank you. No one ever asks me to use one standard error. The directions would say graph a 95% confidence interval. And then they would put, that is your mean plus minus 2 standard error of the means. Okay, so I'm going to do 2 standard errors. Get rid of u. So that's 0.4. That's still 0. Nobody wants 1. This is 0.6, and this is 1.2. Then you know how I work. I've always got to figure out what my error bars are going to be before I actually graph them. So for this one, it's going to be 2.61 plus 0.4, 2.61 minus 0.4. So the mean plus 2 standard errors, the mean minus 2 standard errors. So I've got math going today. So that's going to be 3.01. Yeah, I'm not graphing that. I'll graph 3. And this will be 2.2-ish. Like I can put 1, but whatever. And that's the error bars for this one. The next one has no error bars. We'll figure that one out. Then I'm going to come over here. I'm going to do 2.8 plus 0.6, 2.8 minus 0.6, and I get, what is that, 3.4 and 2.2. Then I'm going to do 6.2, so that's that set of error bars. 6.2 plus 1.2, which is 7.4, and 6.2 minus 1.2, which is 5. There's pretty much variation in that. That's pretty big. So now I'm going to graph all of this. So for my first regular, which is right here, I'm going to graph 2.61, which is the mean. Then I'm going to go up to 3 and down to 2.2. So here about would be 3 there, so that's about what I get. Then I've got this weirdo. Pretty much I'm going to graph 6 because I can't do 5.96. And then I have no error bars. Well, how do I show somebody I don't have any? There. We're going to talk about that. This is for the class now. The class mean for the regular was 2.8, so that's close to what we had. And then my error bars went 3.4, so a little more, and down to 2.2, a little more. And then the average for the double stuff was 6.2, so just a smidgen more than what we had. It went up to 7.4, okay, that's pretty big, and down to 5. Okay. So if you're telling me, okay, I just made you do all this, but nobody ever has to do that. This is what you would get, or you could just get the graph. So let's think about what we would be asked. Let's think about why we did this. The variation when we just did 2 was really small. You only had 2 cookies. How different can they be from each other, really? Oh, obviously not very much. So the error bar size tells me how much variation is in my sample, and there's not much. But I do know this much. I can say for a fact there is a significant difference between the two. If I wanted to argue, well, I'm going to sue them. That double stuff, that's just the same as the regular cookie. No, it's not. These error bars do not overlap. They don't contain the same data. They're totally separate. So at this point, the double is significantly different than the single. That's for just an N of 2. We had an N of 136. That's a lot more cookies. When you have a lot more cookies and a lot more twisting and a lot more things, you end up with more variation in the data within your population. Some people got way down here for the amount, which would be in what, 5? And some people got way up here around 7.4. I mean, we had a lot of variation. However, those error bars still do not overlap. So the amount of filling in the double cookie is significantly different, significantly more than in the single cookie. Neither way are you going to go get a lawyer. So do you get the point of what we're doing for why we're doing this? We want to speak to what's the issue with a small sample size. Oh, well, I don't have very much variation. Well, I bet you don't. You had 2 cookies. Here, you had 136 twists. That's a lot of opportunity to end up with like some cookies I had where the filling was still on the wafer and it was not great. So I would expect, that's what we're going to put over here, is with the larger sample, it would not be strange to expect more variation than you would with just 2. 2 is not a representative sample. So this is where we would be. We could still say that there is a significant difference, right, for both, with the double stuff being significantly more filling. Well, I'm not saying it's double, but I'm definitely saying you're not going to tell me that you can't tell the difference between the two cookies than the regular. Okay? All right. The next thing we did, we went back to the potato lab a long time ago. So for this one, I can't do your data for you. You're going to have to do your own data when it comes to putting it into the class one. But I'm going to tell you a little secret. I really don't care if you go do that. So we'll just do this together. So for your lab report, you did your own potato, right? And you had your same solutions that we've had 10 times. Come on. Okay. So those are your different sucrose solution molarities. And this is going to be the class potato data. So what we did, everybody went into the spreadsheet, really they didn't, they went into the form, and the form put it in the spreadsheet. And so we got class data for the percent change in each one of these solutions on average. So this is the class mean percent change. So if it gained, it's positive. If the potato lost mass, it's negative. And we did that for the whole class. Hundreds of data points. Then I gave the one standard error. And we graphed them. So, let me go find that, and I'll copy them over. So we had 24.8% positive as a gain, only 9.7%. Then we started losing mass. And when you have all those data points, we can see how much variation there is in the population. So one standard error, how much population differences do you have at this right here is 1.3. Then we had 1.8, 1.7, 1.9, 2.5. So what do we do with that? Well, just to remind ourselves, we're going to graph it, just like you did when you did your lab report. Instead of this being percent change, this is going to be the class mean percent change. And I know right here in this weird little place, my x-axis is in the middle. This will be your molarities. And I'll have 0, 0.2, 0.4, 0.6, 0.8, and 1, right? The only thing that's going to be different than what you had is instead of just a data point, you're going to have error bars with each data point. We say that again. I'm going to graph that data point. Then I'm going to, because it's a 95% confidence interval, I'll do 2 standard errors, and I'll have error bars on that data point. And that one, and that one, and that one, and that one, and that one. So let's go through our little process we go through. No, thank you. I don't want 2. I mean 1. I want 2. So that's going to be 2.6, go away. 2, go away. 1.6, go away. 3.4, go away. 3.8, go away. And 5. And then before I start graphing, I'm going to do what I always do. I'm going to come down here in my space, and I'm going to figure out what my error bars would look like. So it would be the mean, which is 24.8, and I'm going to add 2 standard errors, and then I'm going to do the same thing and subtract 2 standard errors. And I'm going to do this in my head, and it's really scary. So that's going to be 27.4, and what's that one going to be? 22.2. That's the first one. Then I've got 9.7, oh thank goodness, plus 2, minus 2, so, well, just kidding, 11.7 and 7.7, right? Yes. Then I've got, all of a sudden I'm going to do negatives, so negative 5.8 plus 1.6, negative 5.8 minus 1.6, so that'll be negative 4.2, and then that's going to be what, negative 7.4. If my math is off, I'm sorry. Then I'll have negative 20.1 plus 3.4, negative 20.1 minus 3.4, so that's 17, so 16.7. And then here, this is going to be minus 3.5. And then the next one, negative 23.4 plus 3.8. Why can't these be normal numbers? And then minus 3.8. And I would have here, so that would be 19.6. 27.2. Goodness. Oh, good, 5. Okay, 27.5 plus 5, negative 27.5 minus 5, so negative 22.5 and negative 32.5. Okay, now that I've done this, I get a feeling for how to do my graph. The tallest I'm going to go is 27.4. The lowest I'm going to go is negative 32.5. So I think I'm going to go in tens. So that's 10, 20, 30. It's negative 10, negative 20, negative 30, and I've still got room here. This will be negative 40. Okay? So let's see. Maybe I'll graph in green so we can see it. I'm going to graph the mean as a data point, just like you did before. So I'm going to put a data point at 24.8. Then it gets its own error bar, goes up to 27.4 and down to 22. Well, that's pretty hard to do. That's pretty little. Okay, I'm going to go pretty much to 10. And then I'm going to go up almost to 12 and down almost a little past 8. So that's still not very big. Now I'm going to be negative. I'm going to go about, what doesn't that figure? It's going to be right about here. So there's my negative 5.8, and I need to go up to about negative 4 and down to about negative 7, still really not very big error bars. Negative 20, and I'm going to go, okay, now we're talking. I'm going to go up to negative 16 and down to negative 23.5. So that one's bigger. 0.8, I'm at negative, what, 23, that'd be maybe right there. And I go, whoa, above the negative 20 and go way down here to negative 27. And then I have negative, what, 27.5, and I go way up here and go way down there. Do not connect your dots, right? So, let's think about this. All of the stuff we just did, it's not difficult. It's not. Any kid could really do the graphing. So obviously that can't be the story. We need to talk about what this would tell me. Here's what this tells me. When we all dropped our potatoes in the water, which is the 0, if I had said, whatever, I don't know, did you mess it up and it was 0.2? Whatever, does it matter? Yes, it matters. These changes in the potato, in the mass, are significantly different from each other. It is different to put the potato in the 0 cup and the 0.2. Okay, let's keep on with that. Is it different than to put it in the 0.4? Yes. That is significantly different than the other two. Okay, keep going. What about with 0.6? Why, yes, it is. All of these first 4 solutions are significantly different from each other, which means that you can't accidentally drop it in the wrong cup and go, whatever, it's not going to matter. It does matter. So as this sucrose concentration in the solution increased, we had a significant decrease in the percent change in mass in all of our potatoes for everybody. Everybody. Now, we started to get more variation in all of our data. Like, we were not as close to each other with what happened to the potato in the 0.6, the 0.8, and the 1. Let's think about that even farther. Don't all 3 of those overlap? So if you had a terrible teacher who said, I don't know. I just made the solutions. I don't remember. What if it was 0.8? What if it was 0.6? What does it matter? Well, you could die. It doesn't. It doesn't. It doesn't matter. There's no significant difference in the percent change once you get here. So let's write what we're saying, because this is what really matters. I'm going to use the orange today. Let's talk about these guys. So this is going to be at a high concentration of sucrose in the solution. There is no significant difference in the change in mass, right? The percent change in the potatoes. Honestly, if you didn't label them, you probably wouldn't hardly know, because there's so much variation. A data point here could just as easily be here, could just as easily be here, because these all overlap. That's not true up here. As you first start from 0 to 0.2 to 0.4 to 0.6, for those, there's a big difference between what cup you drop your potato in. And there's not a lot of variation between all of the 130 whatever different data points we had. All of us had pretty much this same value. Really tight error bars. Tight, tight. Not so tight. But they still don't overlap. So here, at low sucrose concentrations, there is a significant difference in this percent change in the mass of everybody's potatoes, because we're talking, this is all the class data. Okay, that's more what I'm talking about. This graphy stuff, bleh. Understanding the graphy stuff, Okay, how come? How come? That's taking it one more step. Yes, I can tell you these don't overlap, so that means there's a difference. Oh, I can tell you these do overlap, that means there's no difference. Okay, why? So let's think about it. Down here, in this high concentration of sugar in the water, super syrupy, it was a mess. I'm still cleaning it up. The potato loses water to the solution, right? Your little tiny cube of potato only has so much water. So if it's lost a lot of water here, it may not have any more water just because there's more sugar. If it gave all it's got, that's all it's got, right? So we need to think about this here, and we need to put how come. So let's put here, this is our big takeaway. So let's give it a crown. There's a crown. So the reason for this is, there is only so much water the potato can lose. So if I told you, look, here, let me tell you what you're going to do. You're going to go make these solutions, and I don't want it just to 1. You make that up to 2. Oh, God, that's terrifying for me to think about that. But anyway, I'm just going to be ugly. You make that up to 2. I want to see 1.2, 1.4, and let's just see what happens. Couldn't you go, excuse me. I don't think I'm going to do that. I'm pretty sure that, like, it's not going to be any different. Really? Why? Well, because if it's lost all the water it can lose to the solution at 0.6, and 0.8's not much different. In fact, it's no significantly different, and it's not significantly different here. I don't think it can lose any more just because you give it more sugar in the solution, right? I could predict that the data would look just like this. I don't care how much sugar you put in it. That's not true here. Let's see why. Let's think about it. It all has to do with, so what's the molarity of the potato anyway? Well, if these data points really don't matter, right? These are the ones that matter. I can say for a fact that somewhere between 0.2 and 0.4 is the molarity of the sucrose in the potato. That's where there's no change. It's where it crosses this x-axis. So that's my prediction based on just this drawing. But I've got math. And luckily for you, I've already put them in there. So if we go to stat, which is where I went, and I'm going to edit, and what I have my molarities, and then I have just the percent changes of what we put in there. I'm just finding the line of best fit. So now I'm going to calculate my linear regression, and sure, whatever. This is now the equation of my line of best fit. So y equals negative 53.6x plus 19.7. If I say, okay, on the y, if the y is 0% change, so I'm going to solve for 0% change, what would I get because x is the molarity? What would I get for the molarity of the potato? All right, so let's think. How much sugar's in there? So I've got. Nope, clear. Just kidding. 7. Figures. Now, I know this is being too accurate. I'm okay with it. It's 0.37 molar is the amount of sugar in the potato. So, let's think about that. So, 0.3 is about here, so right about there is the molarity of sucrose for all of the potatoes, because this data is for all of the potatoes. It's about 0.37. Well, that makes perfect sense. There's enough of a difference between what my potato is, which is 0.37 molar, to 0.4. I had a little bit of loss to the solution. Okay, that makes sense because it is more. If you go 0.6, I'd have a little bit more. This doesn't help to go higher. If you go less, water does move in. I know there's no way to go past negative or not get over here, but you're going to have a point to where that, again, water can only so much go into the potato. It can't hold anymore. So we're probably maxed out right here because you don't have any sugar in there. So this whole thing, being able to have this conversation about these data points are important. They're valid. I would really use those. Well, wait a minute. Didn't you use all of them for here? Oh, I did. Let's check that. So I'm going to edit, and I'm going to go down here, and I'm just going to get rid of the 0.8 and the 1, because I really don't think that I should use those. Well, let's see how this changes. So if I go do, and by the way, I didn't put this here, but my R was really good at 0.97. So I'll calculate my linear regression, and when I fix it, I get y equals negative 75.1x plus 24.7. So let's see how that changes things. Like, does it? Well, I'll tell you what it does change. That's almost perfect. Like, sneaky, not real perfect. So I'm going to solve for x. I can do it in my head because that's going to be about 0.3, but whatever. So 24, 0.7. That 7 sticks. So you end up with 0.33, and your R value is like stupid. It's not a huge difference at all. And honestly, we can't be that accurate anyway. But it does give you a feel for, it just dials it in a little bit more toward this way. And it would let you have a valid reason for only using those 4 data points. So that's what we did today, and with the Oreos, and with the pyruvate oxidation. So I hope that helps. All of this would need to be in your notebook, just the same. The only thing is, no cookies. But if I have extra when you come back, I'll give you cookies. I will save them for you because I love you. I will see you later. Thank you.